Welcome back, folks, to another edition of The Deep Dive. Today, we're taking off vertically, you could say. We're diving into the really early history of helicopters.
It's a fascinating story. We're drawing heavily from J. Gordon Leishman's book, A History of Helicopter Flight.
Right, and it's packed with these incredible early attempts, some really wild ideas, and the huge challenges these pioneers faced.
Absolutely. And what strikes you right away is that people were dreaming of and actually trying to build helicopters before the airplane really took off.
Before the Wright brothers, even.
Well, certainly concurrently, and with concepts predating them, our source details quite a few concepts, even models, way back. They were serious engineering attempts, not just sketches on a napkin.
Okay, let's get into some of those. The book mentions Bright, 1861, with a coaxial design.
Yeah, 1861, coaxial, so, one rotor spinning above another, going opposite ways.
And the point of that was?
Torque. It's all about canceling out that twisting force. If you have one big rotor spinning one way, the body wants to spin the other way. Two rotors spinning opposite directions counteract that.
Yeah.
Bright was tackling that fundamental problem early on.
Makes sense. Then you mentioned Droid, 1877, twin rotor, steam-powered.
Exactly. Steam was, well, kind of the high-tech power source of the time, so it's logical they'd try it.
Okay. And von Achenbach in Germany around 1874, single rotor. But the book says he might have been the first to use a tail rotor, that little thing on the back.
That's the really interesting bit. It seems he conceptualized using a smaller sideways-facing rotor on the tail, specifically to push against that main rotor torque.
Wow. That's basically the standard helicopter design we see everywhere now, isn't it?
Pretty much. For single main rotor
Wow.
types, yeah. It was a brilliant insight. Without it, the helicopter just spins. Achenbach solved the core stability issue. And interestingly, Messier actually published some of his propeller work decades later, in 1923, shows his thinking had legs.
Amazing foresight. The source also mentions Ladugin in Russia around 1869. His idea sounds different, a main lifting rotor plus another propeller for push and control.
Yeah, another approach, separating lift from forward movement and control, different inventors attacking the problem from different angles, you see.
And Forlani in Italy, 1878, steam again, but dual counter-rotating rotors. And the book says it actually flew. Free flight.
That's the report, yes. Over 40 feet high for maybe 20 seconds. If accurate, that's accurate. Well, that's a pretty big step for a model in the 1870s.
Definitely. But obviously we weren't seeing practical helicopters filling the skies then. What were the big hurdles holding things back?
Two main things jump out from the source. First, just a fundamental lack of understanding about how rotating wings really behave dynamically and aerodynamically.
If physics were too complex.
Extremely. And this lack of understanding led to things like massive vibrations shaking the machines apart, lots of mechanical failures. Designing these high-speed rotating systems without fully grasping the forces involved.
Yeah.
I can imagine. Broken parts flying everywhere. What was the second hurdle?
Engines. Simple as that.
Yeah.
They needed power, but they also needed lightness. That power-to-weight ratio is absolutely critical for vertical flight.
And early steam engines just weren't cutting it.
Generally, no. They were heavy for the power they produced. Getting airborne, let alone staying airborne, was a massive challenge with that kind of tech.
Right. But you said things started changing around 1920. What happened?
A gasoline engine, specifically the internal combustion piston engine. By about 1920, these were becoming much more available, and crucially, they had significantly better power-to-weight ratios.
Ah, the game changer.
Absolutely. Suddenly, you had enough power in a light enough package to make sustained flight seem possible. So the focus shifted. It wasn't just if you could get off the ground, but how you could control the thing once you were up there.
So control became the next big mountain to climb, and this led to a boom in prototypes.
Exactly. The source mentions tons of prototypes popping up globally around this time. Lots of short hops, flights just skimming the ground, what we call flying in ground effect.
And it was truly international. Britain, France, Germany, Italy, the U.S.
Yeah, all contributing pieces. Different countries often led in specific technical areas. But, and this is key, despite all this activity, the really practical designs, the ones that could actually lift a pilot and a useful payload, didn't emerge until much later, in the late interwar period, so, the late 1930s.
Okay, let's circle back to those engines for a second.
Yeah.
You said steam was the early go-to, but inadequate. Can we get more specific? What were the real killers for steam?
Well, the source mentions engineers like Stringfellow and Henson in Britain, and Charles Manley in the U.S. Henson's engine, around the 1850s, actually wasn't bad for its time, maybe 0.06 horsepower per pound. Used methyl alcohol fuel, interestingly.
There's always a but.
The big but was efficiency and endurance. To save weight, these early steam engines often didn't have a condenser, the part that recycles steam back into water.
Ah, so they just vented the steam.
Right, which meant they used a ton of water. The source quotes something like 30 pounds of steam per horsepower per hour. You'd need a huge water tank for any kind of decent flight time. Totally impractical. For Lanny, even with his relative success, was still dealing with these steam limitations.
Okay, so short bursts maybe, but no real flying. What about Charles Manley's engine? You said that was better.
A bit more sophisticated, yeah. Around 1900 for Langley's aerodrome project. It was a 5-cylinder radial steam engine. That radial layout cylinders arranged in a circle was important, kind of a precursor to later air-cooled combustion engines.
None of the specs.
Produced about 52 horsepower, with a power-to-weight ratio around 0.34 hplb. Definitely an improvement over Henson. Progress was being made step by step.
And the book also mentions Lawrence Hargrave in Australia coming up with the rotary engine concept. Not radial, but rotary.
Correct. Rotary means the cylinders themselves rotate around a fixed crankshaft. Another approach to getting power while trying to keep weight down and manage cooling. This design also saw use in early aircraft, even some helicopter experiments.
So many different engine ideas, but the real breakthrough was internal combustion.
Without a doubt. The source really emphasizes this, pointing out it built on decades of progress in thermodynamics. Think Soddy Carnot back in 1824, mechanics, materials. Even understanding liquid fuels better. Bodo Roches figuring out the four-stroke cycle theory in 1862, Nicholas Otto building a working one in 1876. All these pieces came together.
A convergence of science and engineering. So how did the internal combustion engine specifically solve the helicopter problem where steam failed?
Compactness and power-to-weight ratio, that's the key. They were much smaller and lighter for the power they produced compared to steam. Suddenly, you had a power source that was actually feasible for sustained vertical flight.
And we saw these in early airplanes too, right? Like the French Gnome and Leron engines.
Exactly. Air-cooled rotary gasoline engines. Our source cites their power-to-weight ratio at around 0.35 hplb, pretty advanced for the time. Even Igor Sikorsky, whose name becomes huge later, used a rotary engine in a test rig back in 1910.
Interesting. So even though rotary engines had their own issues, gyroscopic forces, fuel consumption, that power-to-weight advantage was just too important to ignore early on.
It was critical. The smoothness and relative lightness made them suitable, despite the drawbacks. So the bottom line is, by the early 20th century, the engine piece of the puzzle was finally starting to fall into place.
Okay, power sorted, mostly. Now let's look at the actual helicopter prototypes from the early 1900s. Charles Richet, 1904, unpiloted.
Yes, a small experimental machine. Not a huge flight success in itself, but significant because one of his students was Louis Breguet.
Ah, the connection again. And Breguet, with his brother Jacques, started their own experiments soon after, 1906. Guided by Richet. They came from clockmaking, right? Precision must have been in their blood.
Good point. That background probably didn't hurt. And Louis Breguet was clearly methodical. Like the Wright brothers did for wings, he did detailed tests on airfoil shapes for rotors. He was digging into the aerodynamics.
And then came their gyroplane number 1 in 1907. The description sounds complicated. Ungainly quad rotor, 4 sets of biplane blades, that's 32 little wings.
It was incredibly complex.
Yeah.
Visually quite something. Had a 48p engine. Reports say it did lift off briefly with a pilot. But pictures and accounts suggest it needed people on the ground holding ropes, stabilizing it.
So not true free flight.
Doesn't seem like it. It highlighted that key problem again, stability and control. Getting it off the ground for a second is one thing, actually flying it is another.
Right. Okay, then the book mentions Boris Yurov in Russia around 1912. His design sounds much more familiar, single main rotor, tail rotor.
It looks surprisingly modern, yeah. The source notes his blades were well designed for efficiency, long and thin, high aspect ratio. But familiar story. He was let down by engine power. Not enough grunt. And mechanical failures plagued him too. So, no sustained flight.
Another case of brilliant ideas hitting technological walls. But Yurov is also credited with proposing cyclic pitch. That sounds important. What is cyclic pitch, simply?
Hugely important. Cyclic pitch is the magic ingredient for control. It lets the pilot change the angle or pitch of each individual rotor blade as it spins around. By doing that, you can tilt the whole rotor disc forward, back, sideways.
And that's what makes the helicopter move horizontally.
Precisely. Gives you directional control. And we should also mention Gaetano Crocco in Italy. He actually patented a design for cyclic pitch even earlier, back in 1906. He understood you needed to vary the blade angle during rotation to control the machine and counter the lift imbalance in forward flight.
Dissymmetry of lift, right, where the
Yeah.
blade moving forward has higher airspeed than the one moving back.
Exactly. Krockow and Yurev recognized that varying the pitch cyclically was the key to overcoming that and achieving real control. It was a massive conceptual leap.
Monumental. Okay, shifting gears. Louis Brennan in Britain, late 1910s, early 20s. His idea sounds unique. A huge single rotor, but with propellers on the blades to counter torque.
Highly unconventional, yes. Brennan was a respected inventor. He used something called servo flaps on the blades for control. His machine actually flew indoors successfully in 1922, even made some low outdoor flights. But it crashed in 25.
And what happened then?
Well, around the same time, the Autogiro was really taking off, generating a lot of excitement and investment. Official interest in Brennan's complex helicopter design just kind of faded away.
Ah, the Autogiro effect again. We really do need to cover those sometime. Okay, but sticking with helicopters. Raul Pescara, Spain and France, early 1920s. Coaxial again, like Bright, but with biplane rotors. 4 or even 5 sets per rotor. That's intense.
Extremely complex, Pescara was laser-focused on control. He used cyclic blade warping, physically twisting the biplane blades as they went around, which was one of the first somewhat successful uses of cyclic control. He even used differential collective pitch for yaw control.
Collective pitch being changing all blades together for up-down movement.
Exactly. So he had cyclic for tilt, collective for lift, and differential collective between the two rotors for turning. Very ambitious.
Success.
Limited. Early versions were underpowered. Later ones with better engines had some controlled flights, but they often ended in crashes. By 1925, he threw in the towel. It just shows how much painful trial and error was involved. So much experimentation, so many setbacks.
Definitely paints a picture of struggle. Now, you mentioned Autogiros gaining prominence. How did that impact helicopter work?
Well, Juan de la Cierva's Autogiro just seemed more practical, quicker to develop results. In the U.S., companies like Kellett and Pitcairn licensed his designs, got Autogiros flying there by 1928. ANECA, the precursor to NASA, spent a lot of time testing Autogiros. Even the early American Helicopter Society Journal gave them significant coverage.
So resources and attention shifted towards Autogiros. Did helicopter work just pause?
Not completely stopped, but it definitely faced more competition for funding and brain power. There were still dedicated efforts, like Georges de Beautazat in the U.S., a Russian emigre. He built this huge quadrotor helicopter for the Army in 1922. They called it the Flying Octopus.
Flying Octopus. Love these names. What was his background?
Strong theoretical chops.
Yeah.
Studied under Zhukovsky, a big name in Russian aerodynamics. He'd even written papers on rotating wing theory. His machine had 4 large rotors, 6 blades each, very wide blades. Control was through collective, differential collective, and cyclic pitch, probably influenced by Yurev, plus 4 smaller control rotors. Talk about complex.
Unbelievably complex. Did the octopus fly?
It did. Made several successful low, slow flights. But performance wasn't great. It was expensive, and the Army was getting more interested in Autogiros, so the project got canceled.
Another one bites the dust.
Yeah. And the really striking thing the source points out is that it took another 15 years or more before any pure helicopter in the U.S. matched even the limited achievements of de Beautazat's machine. That tells you how hard the problem still was.
15 years. Wow. That really puts it in perspective. What about Etienne Omichon in France? Early 20s, also quad rotor.
Similar idea, yeah. Another quad rotor, but Omichon added 8 more little rotors for control and propulsion. The source calls it a perfect example of the cumbrous mechanical complexity of the era.
10 rotors in total. Good grief.
Initially, it was so underpowered it needed a hydrogen balloon attached for lift and stability.
Seriously, a helicopter balloon hybrid.
Yep, but he kept at it. By 1923-24, he had a pure helicopter version flying. It showed some stability, some maneuverability.
And he actually won a prize for it, right? First closed kilometer circuit.
He did. An FAI prize in 1924. Flew 1 kilometer in a circle, took him nearly 8 minutes, average speed less than 8 kilometers. So yes, a milestone, but clearly not a practical machine. Still, it proved sustained, controlled flight was possible, even if incredibly cumbersome.
Progress, inch by inch. Okay, then, Cordino d'Ascanio, Italy, 1930. The book calls his coaxial helicopter relatively successful. That sounds promising.
It was a definite step up. Good control, large, 2-bladed counter-rotating rotors. Importantly, he used flapping hinges and feathering capability, learning from de la Cierva's Autogiro work.
And his control system was different.
Very innovative. He used small, wing-like servo tabs on the trailing edge of the main rotor blades. Deflecting these cyclically changed the main blade pitch for cyclic control, and deflecting them collectively controlled overall lift. Plus, he had 3 small propellers on the airframe for extra control.
Servo tabs. That sounds familiar. Didn't other designs use that later?
Yes, it proved influential. And Descanio set some modest FAI records, altitude around 57 feet, duration almost 9 minutes, distance over 3,500 feet. Tangible progress towards a controllable machine.
Okay, moving north, the Weir Company in Scotland, starting 1932, they tried coaxial first, then side-by-side rotors.
Right. Their W5, the side-by-side one, flew well in 1938, hit 70 an hour at cyclic pitch. But vertical control was done by changing rotor speed, which was a bit awkward. The later W6 used the same layout, but then World War II started and development stopped.
War interrupting progress, another common theme. Now, Germany, late 30s, Anton Flettner and his syncropters. Intermeshing rotors, how did that work?
Very clever design. 2 rotor masts tilted slightly outwards, rotors spinning opposite ways but geared together so the blades mesh, pass through each other's arcs without hitting.
Sounds precarious.
It requires precise engineering, but it works. It cancels torque efficiently and offers good stability. His FL-265, flown in 1939, was huge. It was the first helicopter to properly demonstrate transitioning into and out of auto-rotation.
Auto-rotation, the glide mode for helicopters if the engine fails, that's critical for safety.
Absolutely massive milestone for safety and practicality. Flettner also developed the FL-282 Colibri, or Hummingbird. The FL-282 and the Foch A-266 were actually among the very first helicopters put into limited production, mainly because of the war.
So WWII actually spurred some helicopter production.
It did, for specific roles like observation, and the syncropter idea lived on. After the war, Kellett and Kaman in the U.S. picked it up. Cayman, especially, had a lot of success producing syncropter helicopters.
Fascinating how these different configurations emerged. The source also lists other key U.S. pioneers. From the 40s, Young, Piasecki, Hiller, Kaman. A new generation.
Right, the pace really picked up then. Arthur Young's work was crucial for stability. He developed the teetering rotor.
Teetering?
Allows the 2 blades of the rotor to flap up and down together like a seesaw, reducing stress. But the key addition was his stabilizer bar, basically a weighted bar linked to the blade pitch controls.
What did that do?
It added damping, made the rotor much more stable and easier to control. Lawrence Bell saw the potential, backed Young, and that led to the Bell 30 prototype in 1942. 2-seater, single-main rotor with that teetering system and stabilizer bar.
And the Bell 30 was the precursor to?
The legendary Bell Model 47. The Bell 30 first flew untethered in 43, hit over 70 miles per hour. The Model 47 built directly on that.
And the Bell 47, that was huge, wasn't it?
Absolute watershed. First commercially certified helicopter in the world. Thousands built, over 5,000 in the U.S. Another 1,000+ licensed elsewhere. It's the helicopter you see in MAH, the bubble canopy one. It really brought helicopters into the mainstream.
An icon. Okay, what about Frank Piasecki? The book mentions his PV-2 in 1943 as the second successful U.S. helicopter after Sikorsky's.
Correct. And Piasecki became known for the tandem rotor configuration. 2 large rotors, one fore, one aft.
What was the advantage there?
Lift capacity and center of gravity range. Good for carrying heavy loads. His PV-3, nicknamed the Flying Banana because of its curved fuselage shape, flew in 1945. It led to successful military transport helicopters like the H-21 Workhorse.
So by the early 1950s, things were really maturing. Safer, more reliable, easier to fly, mass production starting. Designs like the Sikorsky S-55 and S-58 represented another leap forward.
Exactly. It was a long, hard road from those early concepts and steam-powered hops. But by the early 50s, the helicopter had definitely arrived as a viable aircraft. It's just an incredible story of persistence.
It really is. Thinking back on everything we've discussed, the journey from those initial, almost theoretical concepts through all the daunting challenges, the engine problems, the aerodynamic puzzles, the control issues, it's just a remarkable testament to the ingenuity and, frankly, the stubbornness of these pioneers.
Absolutely. They were tackling incredibly complex problems with, comparatively primitive tools and understanding. The perseverance is astounding.
It really makes you appreciate the machines we see flying today.
And here's a thought to leave you with. How might those very limitations they faced, the specific struggles with engine power or materials or control methods, how might those roadblocks have inadvertently pushed development down certain paths? Could those constraints have actually shaped the wide variety of helicopter designs we see today, like coaxial, tandem, syncropter, single rotor with tail rotor?
That's fascinating. Did the problems dictate the diverse solutions? A great question to ponder. Well, that brings us to the end of this deep dive. Thank you so much for guiding us through that incredible history.
My pleasure. It's a story worth telling.
And to all of you listening, if you found this journey into aviation history as interesting as we did, please do us a huge favor. Hit that like button, subscribe to the deep dive if you haven't already, and maybe share it with someone else who loves this stuff.
Yeah, your support genuinely helps the channel grow and lets us keep bringing you more deep dives like this one.
Thanks again for joining us, and we'll catch you on the next one.